It is a pleasure to introduce Dr. Raquel Perales from Center of Research in Mathematics in Guanajuato, Mexico. She's, of course, the winner for the IMSA Latin American Mathematics Research Prize for Young Investigator this year. And she will be speaking about convergence of manifolds and metric space. Raquel.
Thank you for having me here. And let's start my talk. So I'm going to talk about convergence. So I'm going to say what is metric spaces, and then the two types of distance that I care about, and they are called Gromov-Hausdorff and Intrinsic Flat distance. So usually I would say VH and IF distance. And then I do Riemannian geometry. So what I care about are manifolds. And what we're going to do is what's the difference between these two distances, and can we ensure when a sequence of manifolds converge to the same limit using either Gromov-Hausdorff or intrinsic flat distance. And we will speak about manifolds with boundary, which are very different from two manifolds with no boundary. And at the end, I will talk about convergence of manifolds with scalar properties lower bounds. And if I have time, I will talk a little bit about each limit and RC space. So this talk, I'm not going to give too many details. I'll just tell you what I've been doing the last years. Okay. So as everybody knows, a metric space is a set with a distance function that satisfies these three important properties. And we are going to say that a sequence of elements in this metric space converted to a point in this metric space if the limit of the distances between Cj and C converges to 0 as j equals to 0. And the two examples, so these are trivial examples, is the Euclidean space of dimension 1 with the distance that we all know. So absolute value between the two numbers. And there I also picked the two sequences that converge to some numbers. And my second example is the space of continuous functions that are defined in the interval 0, 1, and we can put this distance, the supremum distance. And in the picture, you can see a sequence of manifolds, a sequence of functions that are converging to a limit function that is depicted in field color. Okay, so these are the easy examples, and let's pass to more general examples. So given a Riemannian manifold, so it has a Riemannian metric that is denoted by G, and we can define the distance between 2 points in the Riemannian manifold. And this is going to be the infimum of the length of all the curves that join the point x to y. And here the curves, we can take them to be visual multipliers. And so with this definition of distance, our manifold is going to become a metric space. And okay, so here I start with the definitions that I want to study, which is Gromov-Hausdorff distance and intrinsic flat distance. And for the moment, I just want to say where they are defined. So they are defined, sorry. Okay, I need to learn how to use this. So they are defined in the class of compact metric spaces, that's for the Gromov-Hausdorff distance. And in particular, as I told you, what I'm going to care about are Riemannian manifolds. So I will study compact Riemannian manifolds. That's going to be the class that I want to study with the Gromov-Hausdorff. And for the other distance, it is defined in something that is called compact integral current space, which just means, well, this is a long definition, but just think that the first two entries are a metric space, and this D is a way of integration and or orientation. And so I'm going to restrict this distance to the class of compact oriented Riemannian manifolds. So, and I'm going to compare this type of these two distances. And before telling you more details about the definition of this distance, I want to show some examples about sequences that converge. And you can see here, you can think of this as a sphere, and this is like a line. And what is happening to this sequence of manifolds? Think that they are manifolds here in the corners. I probably didn't draw them correctly, but this sequence of spheres will converge in Gromov-Hausdorff sense to this sphere with a segment attached, but with intrinsic flat distance converges only to the sphere. Okay, so what you get to see here, and this is going to appear in the other examples, is that if we are losing volume, then we don't get anything with intrinsic flat convergence. And here we are getting some stuff because here we have, like, you should think about the distances are, well, yeah, this is more about distance and this is more about volume. You will see later on the formula for the Hausdorff distance and the flat distance. And then in this example, well, this sequence of manifolds are converging to the circle because these tori are collapsing. And here we do have intrinsic flat convergence, so I didn't write it. And the intrinsic flat convergence will be to something that we call the zero space. So zero integral coordinate space, and that's because we lost. So if you think of this as two-dimensional, then we are dropping to one dimension. So we lost all the two-dimensional volume. So then our limit space is called zero integral coordinate space. And in this example, these are spheres, and they have many splines. So, and they are getting thinner and thinner and thinner, so I can put more and more and more. And if I put the length distance to this manifold, with Gromov-Hausdorff distance, they won't converge because they are becoming less and less compact spaces. While for intrinsic flat distance, these lines are becoming thinner and thinner and thinner, so the area is getting smaller and smaller, or volume is getting smaller and smaller, so in the limit they disappear, as in this example. Okay, so I'm going to discuss the definition of Gromov-Hausdorff and intrinsic flat convergence now. But if you already understood from the pictures what I'm doing, you can skip the next part and come back when I finish the definition. So, what is Gromov-Hausdorff distance? Well, as I told you, this distance is defined between two metric spaces. And, well, some people say that Gromov defined this distance, but also appear in the work of other people. So, but I don't wrote Gromov, so don't feel bad to think that Gromov didn't define this distance. So, we have two metric spaces, and look at the picture. So, I have metric space M0 and M1. And what I have to do to calculate their Gromov-Hausdorff distance is putting them in a bigger space. So my bigger space here is set, and I'm going to put them, this M1 and this M0 in set, using a map that preserves the distance. And once that they are inside this bigger space, I will take the Hausdorff distance of the images, phi1 x1, phi2 x2, and take the infimum over all possible maps and all possible complete metric spaces in which I'm embedding my metric spaces. And the definition for intrinsic flat distance is very similar, but remember that here our spaces are these triplets, so these integral coordinate spaces. And what I'm going to do is, again, put these spaces inside a bigger space using a map that preserves the distance. So here, but because we have this extra parameter, we actually push forward this parameter, which encodes a lot of information of our integral coordinate space. And once again, we have to take, well, here now we have to take the flat distance in this space set and take the infimum over all possible isometric embeddings and all possible spaces in which we can isometric embed these currents. Okay, so that's the definition. But you are wondering, okay, what is Hausdorff distance and what is flat distance? I'm going to say that in 2 more slides. But before that, let me just tell you something. So I was lying a little bit when I said that Gromov-Hausdorff distance is defined for compact metric spaces. It's actually defined in an equivalent class of metric spaces, because the distance is actually between 2 metric spaces is going to be 0 even only if the spaces are isometric. So we are actually thinking of these equivalent classes of isometric spaces. And the same happens for the intrinsic flat distance. Well, something very similar. So 2 integral current spaces are going to have intrinsic flat distance equal to 0 if there is an isometry between them, and also the push forward of the current T1 has to be equal to T2. And this, for manifolds, means that we have an isometry that preserves the orientation of our manifold. Okay, so the theorem is just what I told you, that if we take this equivalence class by isometries or by isometries that preserve the orientation, then what I'm talking about, these distances are actually distances. Okay, and finally, what is Hausdorff distance and what is flat distance? So for this, remember, we are fixing a metric space set. And I'm going to write that it is complete. And then the definition of Hausdorff distance between 2 sets in this metric space set is as follows. So look at the picture. So you can think of the red line. So it's a subset of R2. And this is A1. And then the blue line, you can think of it as A2. And I want to calculate the distance between this red line and this blue line. So what I have to do is take tubular neighborhoods around A2 or around A1 and make sure that A1 is contained in this tubular neighborhood around A2. So basically, if I want to draw a tubular neighborhood around this red line that contains this blue line, the radius that I have to choose is the height of this kind of wave. Okay, and then I have to take the infimum of all those possible radius. And now the other distance, which is the flat distance between 2 currents, is as follows. So again, think of the red line. So this is a manifold. It has an orientation. Here I draw the arrows showing the orientation. And what we have to do is to come up with, let's say, I'm going to say manifold, but this can be more general. So a manifold of higher dimension, so of dimension 1 higher. So this is going to be dimension 2 in this example, and something of dimension 1, such that we satisfy this quantity. So actually here our manifolds, the V1 and the U1, will have to be oriented. So I put the arrows here, and they have to satisfy this equation. And this equation is kind of a Stokes theorem. So you can orient this in like counterclockwise, and then you will get this. And then you have to orient these green parts. Okay, and once that you have this V and this U, what you are going to take is the mass, that's just the volume. So in this case, it's going to be the length of the green parts, and then the area of the yellow part. And try to take the infimum over all possible choices of U and V. So now here you see that with intrinsic flat distance, what we are trying to do is minimize the volume that we have. And let me mention something. because I remember that people talk a lot about cobordism the first day. This looks a little bit like cobordism, but the thing is that T1 and T2, they are functionals, so they can be the functional equal to 0, which that doesn't happen when you are talking about cobordism. Yeah, because many times people ask me, oh, does it mean that T1 and T2 are concordant? Well, maybe if you can allow this empty manifolds or functionals that are equal to 0. So now let's continue. So now you know what is intrinsic flat distance and Gromov-Hausdorff distance. So you can come back. So this is the end of my definition. And now I'm just going to tell you what I've been working using these definitions.
Excuse me.
Yes.
In which space the notion of integral five makes sense?
In which space? In which space?
In any metric space, the notion of.
Yeah, complete metric space. That was first defined by Ambrosio and Kirchhoff, and then they define it for like compact case or when the mass is finite, and then it was generalized by Urs Lang and by Lang and Wenger for pointed, let's say pointed integral current spaces in metric space. Okay. So what are the questions that I've been trying to solve? Whether does a GH and IF convergence sequence have same units? And GH and IF convergence of manifolds with the boundary. I told you boundary is a little bit different to having manifolds with no boundary. And what about convergence of manifolds with uniform scalar curvature bound, lower bound? Another question, what is the geometry of Ricci limits? And more in general, what is the geometry of RCT spaces? And here RCT spaces contain Ricci limits. Okay, so let's address these questions. So we want to know where Gromov-Hausdorff and Intrinsic Flat sequences agree in their limits. And there is this powerful theorem by Sormani and Wenger that says the following: if both limits exist, then the intrinsic flat limit is smaller than the Gromov-Hausdorff limit, smaller or equal. And here I have the picture that shows this scenario. So here we have the sequence, it has both limits, and the green limit is smaller than the blue one. Okay, so we know when we have this containment, and now let us see when we have a Gromov-Hausdorff convergence and intrinsic flat convergence. So Gromov-Hausdorff convergence is actually, as I told you, for metric spaces, and we have to put restrictions to our metric spaces. So they have to have a diameter bound, and they have to be covered by at most n epsilon balls for each epsilon greater than 0. So once that we impose these two conditions, we get a compactness with respect to Gromov-Hausdorff distance for this class of compact metric spaces. And the theorem of Wenger, which works for integral coordinate spaces, what you need to impose in order to get compactness is the following. So you get, again, a diameter bound, and then you replace this compactness condition by a volume bound and a volume of the boundaries uniform bound. So with these two more conditions, together with the diameter, to get a compactness within this class of n-dimensional integral coordinate space. Okay, so, and we want to start manifold. So what happens for manifold? Well, if I impose reaching lower bound, so here, I think, yeah. If I impose here a reaching lower bound, so reaching greater or equal than k for all my manifolds, then as I told you, I have to impose a diameter bound, then I will get a free compactness with respect to the Gromov-Hausdorff distance. So I will get subsequences that converge, but the limit is not going to be necessarily a manifold, it's just a metric space. And here, what I'm considering are manifolds that do not collapse. That means that the volume is uniformly bounded by some constant B. And these limits are called, as I told you, Ricci limits. And when I impose this volume condition, they will be called non-collapse. So it cannot happen that this tori converge to a free. Okay, so now we are in a position to study when Gromov-Hausdorff and intrinsic flat limits agree for manifolds with Ricci lower bounds. And this is the theorem. So here I put a lot of terms together. This is just a list of what we know up to now. And the first people that investigated this question was Sormani and Wenger, and they showed that they agreed for Riemannianmanifolds with Ricci non-negative lower bounds. And of course, as I told you, they have to be orientable in order to use intrinsic flat convergence. They have the diameter bound and the non-collapsing assumption. And then I studied a similar class of manifolds, but these manifolds have boundaries. And then I have to add some conditions to the boundaries in order to get Gromov-Hausdorff compactness. You saw in the theorem of Wenger that it's very easy to get intrinsic flat convergence. You only need a bound on the volume and a bound on the mass, and the bound on the volume of the boundaries. So it's easy to get intrinsic flat convergence for manifolds with boundary. What you need is more conditions to ensure that this manifolds with boundary converge using Gromov-Hausdorff distance. So that was my first paper. And then Madrid and Portuguese generalized the work of Sormani and Wenger, and they just proved this for Ricci lower bound. Then Portuguese and Sormani proved that these limits agree for some spaces that are called tetrahedral, that satisfy tetrahedral property. And with Núñez and Bron, we generalized this definition. We gave some examples saying that the first definition, the Portuguese Sormani definition, wasn't that good. And we introduced this new definition and proved that in this case, the limits also agree. And finally, with NaN-Li, we show that these limits agree if you have Alexandrov spaces with no bound. And well, this last word comes from another word that I have in other collaborators. So these are the results of GH equals to IF. And now let me tell you a little bit about this manifold with boundaries that I've been talking about. So here I have a sequence of manifolds. And look that they are actually flat. They have a diameter bound, and they have a volume bound. But this sequence of manifolds don't converge in Gromov-Hausdorff sets because I have too many pedals. If you think of it as flowers, I have increasingly many pedals, and that tells me that the spacers are becoming less and less compact. But and the problem here is that we do have boundaries. Okay? So what should we do if we have manifolds with boundaries? And the story started in the following way. So first there was a work of Kodami in the 1990s, and he proved Gromov-Hausdorff convergence for a class that has double-sided bounds in the sectional curvature. And for the boundary, it requires boundary to be convex, basically, and non-collapsing border bound, and some boundary inject. And then from these three conditions, we got boundary injectivity radius bounded by some number, and another interior injectivity radius bounded by another number. So, but actually, this condition, like a bound on the sectional curvature from below and from above, is too much. So then there came other works, and for example, there is this work of Anderson, Katsida, Kubilev, Lassas, and Taylor, but they studied C1 alpha convergence. And of course, because they want to have C1 alpha convergence, they have to impose like injectivity radius bounds, and also injectivity radius bounds for the boundary. And then one came and he relaxed actually the condition of Korani a lot and only imposed a rich lower bound, which is the type of results that we would like to have. A diameter bound, and the boundaries have to have a second fundamental form bounded below and above by some numbers. And then there is Knox in 2012, but he got the alpha and 1p convergence. And then I came, and when I came, I started working with Sormani, and we defined something that is called a new limit. So here we have manifolds with boundary, and what we study is not the convergence of these manifolds with boundary, but of regions of these manifolds. So actually, this M delta that you see here is to take the points into manifolds that are inside the manifold and that are away from the boundary by delta. And once that we are away from the boundary by delta, you have a new sequence of manifolds, and you study if they converge. And then you try to take delta to 0 and see if all these limits converge to the actual limit of the original manifold. Okay, so that was one work that was from 2014, and then I included other convergence results for manifolds with boundary. So one for intrinsic flat convergence, and I'm going to tell you a little bit about it later. Then this result that I just told you about, that intrinsic flat and Gromov-Hausdorff limits are both equal, and then this result of intrinsic flat convergence. And the important thing in this work, and also the work of Müller, is that these last two results do not require bounds on rich curvature, which is going to be important in order to use it when we have manifolds with scalar curvature lower bounds. So, what is the type of result that I drew for intrinsic flat convergence? Well, in order to have intrinsic flat convergence, I told you you have to bound the diameter of the manifold, and you have to bound the volume of the boundaries and the volume of the manifolds as well. So I can impose rich non-negative and some mean curvature lower bound, and I will get intrinsic flat convergence. So that's one result. And the other result is this of myself with Allen. And this is actually a generalization of some work with Allen as well and for manifolds with no boundary. So let's read what this theorem is about. So what we're doing in this theorem is we are fixing a topology. So we fix a Riemannian, we fix a manifold M, and we are going to endow this manifold with a fixed Riemannian metric. So this is G0. And what we really want to do in this theorem is to say our sequence is going to converge to this Riemannian manifold, M with G0. So here, read the last part of the theorem. So we have a sequence, and it's going to converge to this manifold that I'm prescribing. So what do we have as elements in this sequence? What we have is the same differential manifold, but we have here another Riemannian matrix. And this Riemannian matrix actually can be just continuous. This one has to be smooth because of the applications that we want. Actually, it can be C2, but this one can be only continuous. And besides, once that we have the sequence, we require some conditions on our Riemannian matrix. And that is that the distances with the Riemannian matrix G0 are smaller than the distances with the other Riemannian matrix. That the diameter is bounded, which is a natural condition to have intrinsic flat convergence, and that the volumes converge to the volume of the manifold that we want to converge. And we need some boundary conditions, and this is just like kind of volume condition of the boundaries. This is going to tell us that the boundaries have uniform bounded volume. And then, once that you impose this condition, then you get that MJ converges to N0. And it's the whole sequence. You don't get a subsequence that converges. Actually, the whole sequence converges. Okay, and I mean, this can be relaxed a little bit. And for the case which manifolds with no boundary, of course, you don't need to ask the requirement of the Riemannian tensor restricted to the boundaries to converge in this way to 0. Okay. So, since I just told you about this theorem that doesn't have any which go down, I want to pass to convergence of manifolds with scalar curvature lower bounds. And in this picture that I've been talking a lot is we have these spheres. And I have a sequence of spheres with splines that are getting thinner and thinner and thinner. So I have here my first element of my sequence. So this is this sphere in gray. Then my second sphere has 4 splines, and the third one has 1, 2, 3, 4, 5 splines, if I'm counting correctly. And these manifolds, if you think of them as 3-dimensional manifolds, you can put a metric such that the scalar curvature is bounded below uniformity. But as I told you, this sequence is not going to converge in Gromov-Hausdorff sense, nor C0 and the C0 limit is not going to exist. But the intrinsic flat limit does exist. So there are very nice and famous theorems. One of them is this by Shane and Yao and Gromov and Lawson, and they prove the following: that any n-dimensional torus with a Riemannian metric G and with non-negative scalar curvature has to be a flat torus. So then you ask yourself, okay, what about if I have a sequence of tori and the scalar curvature is becoming increasing to 0? Like, what is going to happen to this sequence? Is it going to converge to a flat torus? And well, if you use Gromov-Hausdorff distance, you get a lot of counter examples. So that's why you need to use intrinsic flat convergence. Or if you want to use Gromov-Hausdorff distance, you have to impose extra conditions to get rid of these counter examples. So together with Cabrera Pacheco and Ketterer, we also have to impose some conditions to our sequence of tori, and this is just like a diameter bound, and this is probably an area bound, so I forgot about this. And if your sequence satisfies what I told you, then the scalar curvature is converging to zero, but it's negative, then there is a flat torus to infinity, and you have that your tori are converging in intrinsic flat sense to this tori, and the volume torus, and the volume of our tori converges to the volume of our limit. And this class is inspired by the work of Wewill and Sormani that I'm going to mention in the next slide. And well, and the proof of this theorem is actually very, very easy once that you come up with the right class of theorem. You only have to show appropriate volume estimates and then apply the work of Perales and Sormani. So it's this convergence theorem for manifolds with no boundary. And the last theorem, well, this is the last theorem of scalar curvature that I want to mention, is the following. So there is another very famous theorem by Shen-Yao and by Wewill, and here I'm just writing the rigidity case. So the rigidity case says that any complete asymptotically flat Riemannian-manifold, and here I'm writing dimension 3, but this also works for dimension higher than 3, with non-negative scalar curvature has to have, has to have, if I say the classical positive mass theorem, then it has to have a mass greater than or equal to 0. And in the case where this mass is 0, what you get is the median space. So once again, you ask yourself, okay, what about if I make this condition, so the median mass condition, weaker? And that means, what about if you take a sequence of manifolds whose median mass is converging to 0? And do you get in the limit Euclidean space? And the answer I think is if you use Gromov-Hausdorff distance, you will get a lot of sample examples. But if you use intrinsic flat distance, you more likely will get convergence to Euclidean space. And so we again came up with well, actually, this class was defined by Wewill and Sormani, and there was some gap in their proof. So then I came in and we fixed the gap. And so with Allen, I proved the case where the manifolds don't have boundary. So in this example, we will have this. And then Wewill and Perales, we solved like the whole theorem. And with the mean, I gave another solution, or we gave another solution to the convergence of this type of manifolds. So again, we have a class of manifolds that depend on some parameters. We take a sequence there, and we assume that their ABM mass is converging to 0. And then here, I mean, we would like to say this MJ converges to Euclidean space. But my intrinsic flat distance is only defined for compact manifolds. So because it's only defined for compact manifolds, what we have to do is intersect our manifold. And our manifold, we can see it as living in Euclidean space of 1 dimension higher. So it's in Rn plus 1. And we intersect it with this cylinder. So here I have these vertical lines. And then we can study the convergence of these regions. And these regions are going to converge to balls in Euclidean space. And this cylinder, it doesn't matter the radius as long as it's big enough. All the balls are, all these regions will converge to balls. Okay? So are there any questions? If not, then we just end up with what about Ricci units, and in particular, or more generally, RCD spaces. And RCD spaces is a generalization of the definition of a Ricci lower bound plus a dimension bound for metric measure spaces. So here I have XD, that's a metric space, and M is a measure. And in order to define what is Ricci greater or equal than K, well, at the beginning people used optimal transport, and here optimal transport is annotated hidden. This is a second definition, which is equivalent. And if you know about Riemannian geometry, there is this Wagner inequality. So actually, you can ask to do metric measure space to satisfy a good Wagner inequality. And you can see here that this N, which will play the role of the dimension, appears here. That's why in the definition of RCD, you need to impose a dimension bound and a Ricci lower bound. So you have to make sure that this with Wagner inequality is satisfied. You have to impose that your measure M is nice enough, that the W1 space of XDM is also nice enough, and that W12 is a Hilbert space. So with these four conditions, you have that XDM is an Arson space. Okay. So what do we study in RCD spaces? Well, you can create a theory of RCD spaces, or you can say what results that hold for manifolds also hold for these metric measure spaces. And here I have just two examples of such results that hold for manifolds with Ricci lower bounds, and that were generalized with collaborators by myself. Well, by myself with collaborators. So let's read the first one. This is a Chile-Colvin theorem from 1987, and it says that if you have dimension greater than or equal to 3, there exists an epsilon such that if this quantity, so this is a Ricci lower bound, but you have to multiply it here by this diameter squared. And then this quantity is scalar invariant. So if this quantity is greater than or equal than this minus epsilon to the n, so it's almost flat, like Ricci flat, and the Betti number of your manifold equals n, then actually your n has to be bipolar one flat root. And I generalized this with Mondello and Vino recently. And another such example of theorem that works for manifold is this. So you have a manifold, and here the dimension is important. Well, in this example, the dimension wasn't important for this epsilon. Well, you have a manifold of dimension n, which is closed, and you have this Ricci lower bound. So it's bounded by minus n minus 1. Okay, and then you define this thing that is called the volume entropy. And volume entropy is just defined, take ball in the covering space and make the radius of this ball to be larger and larger and larger. Take the volume, take the logarithm, divide by r, and take the sup. So if this volume entropy equals n minus 1, then actually this the covering of this manifold, the universal cover of this manifold, has to be the hyperbolic space with constant probability minus 1. And with Cornell, Dye, Nunez syndrome, Suarez Rato, and Gray, we extended this or generalized this with RCD space. The proofs are much more involved because we are in metric measuring spaces, and they require much more analysis.